was a time when if you had cows and I had 7 cows, pretend these are cows, please, and we wanted to know how many cows we had together, what was the most effective way to compute that? Yes, you would bring your cows to me and we would count how many there were together. You had to bring your entire herd over. Have you ever tried to count cows?
Yeah, that's not easy.
It's not easy. So eventually people noticed that like when you had these 4 things and these 7 things together, that you could just combine them, and they started to express this as 4 plus 7 is equal to 11. And they started to notice properties of how this worked. They needed symbols to represent this. And so they came up with this notion. First of all, there were the Romans, Europe, who said, let's do it like this. How did anybody do anything? I have no clue how anybody's able to do math with this representation. 1 plus I is equal to IV. What is L? 10 is L. There were these other symbols of competing numbers that sort of migrated westward from India, but they actually came to Europe from the Abbasid Caliphate, which we talked about before, called Hindu Arabic numerals. And they're far superior in terms of representing this information because you have something like 1, and you have something like 2, and something like 3, and something like 4, something like 5. And what this tells you right away is you can see what the number is supposed to represent, because the number of interior angles on the shape is equal to the number of things you're trying to represent. So here I have 1 interior angle that tells me, hey, there should be 1 of these things. Here I have 2 interior angles that tells me there should be 2 of these things. I have 3 interior angles that tells me there should be 3 of these things, and so on. And if you're wondering what happened with 7, why doesn't 7 line up? Well, originally 7 was written like this. So you had 1, 2, 3, 4, 5, 6, 7. And there were some weird rules, because if you try to count the way it's written now, it doesn't line up perfectly, but they may have been written differently originally, and when they did, it lined up exactly. So that brings us to the fact that when we encode these numbers, we're trying to communicate information. And the way that we write numbers in our current system is completely arbitrary. It's effective and it's efficient, but it's not something, it's something that human beings gradually developed, like a language. And then you start to think about, well, what happens if we represent something like 32? How do I know that this says 32? Well, what does the 3 represent? 3 tens. There's a ones place and a tens place. And if you were trying to make a physical representation of this, you would have your ones and you would have your tens. Man, you would have 3 of these. So we have 30 here and 2 here. And then if I look at something like 546, what does the 5 represent? Hundreds. So I have 5 hundreds, 4 tens, and 6 ones. Now let's think about this. If I've chosen 10 as my base here, I've said I want to express things in terms of 10, then what's the relationship between 10 and 100? There are a lot of relationships, but one of the relationships is that 100 is 10 squared, right? And another relationship, what if I want to look at a larger number? What if I want to look at 7,362? Ones place, tens place, a hundreds place, and a thousands place. So the thousands, I have 1,000. That's equal to 10 raised to the what power? 3. So 1,000 is 10 to the third. 100 is 10 squared. 10 is 10 to the 1. And 1 is 10 to the 0. I have 7,300, 6 tens, and 2 ones. I could rewrite this as 7 times 10 cubed plus 3 times 10 squared plus 6 times 10 to the 1 plus 2 times 10 to the 0. What do I need to put in parentheses? No, I don't need any parentheses. Every 10 cubed is 1,000. Every 10 squared is 100. Every 10 is a 10 to the 1. And every is a 10 to the 0. There was a time when people didn't have any ability to represent large numbers, but these are equivalent ways of representing the same thing. And this is called base 10 because you're working with 10 as the starting point of everything. Now, do you have to use tens? You can pick whatever base you want. You don't have to use 10. We use 10 because there are 10. We have 10 fingers. What if instead of using 10, we said, I'm going to represent this using twos? So we could just as easily talk about a base 2 system. And if we thought about a base 2 system, then our things that we would be using would be how many ones are there? How many twos are there? How many fours are there? How many eights are there? How many 16s are there? And this keeps going up. How many 32s are there? How many 64s are there? And so if we think about this, we could write something in this notation. But if I just write a string like this, how do you know whether it's base 10 or base 2? You don't. So what you do to indicate that you're using a base 2 number system is you write a 2 as the subscript. And that tells you, you should interpret this in terms of powers of twos. So when I read this, the smallest one is still going to be a 1. Tells me I have 1, 1. What would the next place be here? Twos. Instead of tens, I have twos because that's the next thing in terms of my base. So I have ones, I have 1, 2. What would the next place be? Fours, you say? You say fours? But I don't have any of those, so I don't write anything down. And what would the next place be? Eights. So that means I have 1, 8 I need to add in here. So this would represent the number 11. And when we write in base 10, we just don't write any subscript. Now, this is a terrible example because all you see are ones and zeros everywhere. So let's do another one. Y'all give me a string of binary and let's see if we could convert it to our normal base 10 representation. We said 1, 1, 0. 1, 1, 0, 1, 0. So I'm going to write this out a little bit bigger so I have a place to show where everything is. What's this place? This is the ones. It says there are no ones. There is 1, 2. So I have a block of 2 here. What would the next placeholder be? Fours. So I don't have any fours. What would the next placeholder be? 8. What would the next placeholder be? 16. 2 plus 8 plus 16 is 26. Is that right? So this binary number would be equal to 26 in our normal base 10 representation. Does this make sense? So what if we looked at something like 1, 0, 1, 1, 1? Could you tell me what this number would be? Base 10 representation. Double check what you input. 23. Okay, do y'all see how we got 23 here? We have 1, 1, 1, 2, 1, 4, and 1, 16, and no 8. So this is the same thing as 1 plus 2 plus 4 plus 16, which gives us 23. So that's how computers represent numbers. When you represent a number in a computer, you're only going to be seeing ones and zeros, and there are different ways of representing it.